Cool. Let's get into business. Unless there are other questions. Yeah. Shh. Guys.
If you were to ask us to prove why DFCLs are closed over complement,
Guys. Shh.
how would we go about stating that in a sentence?
What do you mean, like DCFLs are closed and under like if I wanted to ask, if you wanted to say why they're closed under that'd be way too difficult to enumerate that. But like if I wanted to, like those true and false type questions, like are DCFLs are closed under union, and then the answer is false. And then you just give the two counter. Yeah. So things that are way too long on the test to put in a small amount of space, I avoid those like the plague. So every single answer I guarantee is very short on the test. So some people had a lot of issue with writing way too much and saying no time for the other questions. I mean that you should not have that much time for each question, so don't write too much. In some of them I said, I put all this, I marked a certain section that said unneeded, because it's not needed to say like, for the pumping limit question, we need to look at all decompositions X, Y, Z such that X, Y to I, Z is an L for all I and all that nonsense, right? You don't need to say that because I know that stuff. So you don't need to tell me that information. It's not going to help you, okay? Another thing about problem set 6 about the DCFL stuff, I made some updates to the problem set because there were some inaccuracies. Namely, the extra credit question is wrong. So I just don't do the extra credit question because it's not possible. And the alphabet for the DCFLs I changed to 0, 1, 2, which should make the last problem a lot easier, where you have the x, y equals z. So that should be a lot easier. Any other questions? Although the alphabet's not really needed, but it's just to work with that last question. Any questions about the problem set? Okay, so let's see. Let's kind of revisit this question. This famous non-context-free language, right? 0 to the n, 1 to the n, 2 to the n. Could a Turing machine actually decide this language? Yeah, that's not that hard. You just mark a 0, mark a 1, mark a 2, go back, mark a 0, mark a 1, mark a 2, and you just keep going, and then see if you have unmarked 1s and 2s at the end. Pretty simple. So, but this is not even context-free. So it seems like we can get a Turing machine to do this, but not a context-free grammar. So in fact, you can come up with many languages like this: primes, prime lengths, squares of a certain length, though one on the P set that are powers of 2 in length, right? There are many non-context-free languages that seem really easy on a computer. And moreover, like for this language, for instance, how long does it take to verify such a string like this? Well, I mark, so the input is of length, let's say 3n, then I mark 3 characters at a time, and I take order n time going forward and going back. So that's actually an order n squared algorithm to actually decide this language, right? So if I have, so I see puzzled looks already, which is not good. But let's see. So what was our algorithm? It was to mark a 0, then go over, mark the first unmarked 1, go over here, mark the first unmarked 2, then zoom back, right? How many passes going back and forth am I doing? How many passes? Well, in order terms. Order n, right? So we have order n passes going, shuffling across the input. How long for each pass? So I'm going over the input and then I'm coming back. How long does that take? Well, if the n is the length of the input, well, I'm going roughly the input one way, roughly the input the other way, so order n in some sense. So each pass takes order n transitions of the Turing machine to do this. So in fact, order n passes, order n time for each one of them. This language can be decided in order n squared time, which is kind of cool. So let's see. So this is actually relatively quick, right? So we can think of runtimes that are much larger than this, maybe like exponential time, and then even larger runtimes. And then eventually we go to all of decidable languages, solvable in any finite amount of time. And then, of course, we have undecidable after that. So there seems to be a pretty big gap between what we can do with context-free languages, or DFAs for that matter, and all of decidable languages in any finite amount of time. So hopefully let's try to bridge that gap and try to get some languages in the middle between context-free languages that can recognize quite a few but not very many languages to all of decidable languages. So what we're going to, so we first looked at Turing machines in the most general sense. Then what did we do? We talked about LBAs, where we tried to restrict the input to, restrict the tape to where the input is. So we're not going to use any more tape than what was given to us on the input. Then we said, well, that's not enough of a restriction. Then we said, let's go all the way down to DFAs, but then we realized that's too much of a restriction. So then we bumped up to PDAs, where we have, in some sense, we could look at the last character on the tape and then pop off that character or push on another one. Here what we're going to do is, instead of allowing you to run for as long as you want, we're going to restrict how long you can run. Okay, so I'm going to restrict how long the Turing machine can actually run. So in some sense, the Turing machines we're going to talk about now are definitely deciders, because we can just run for the maximum time if we need to. So then we can just say, well, what languages are decidable in this amount of time versus languages not decidable in that amount of time? So other than time, what is a possible restriction we may consider? An amount of space. If we're talking about like big data or something, then DFAs, how much space do they use other than the machine itself? Well, not nothing. Well, it needs to look at the state that it's in and the next character. But does it need to look at anything else? Well, the transitions, but the machine is fixed in this case. So the machine's fixed, so we can assume a constant size because it'll always be fixed. I can just look through the transitions and then find the one I need, and then just update the state that I'm in and the character I need to read. So in fact, DFAs only take constant amount of space. So in fact, this seems like a good restriction because it has real applications, and it's actually an interesting question about the relation between context-free languages and decidable languages. So what we're going to talk about first is time complexity. How much time does something take? So let's define the following set of languages. So time of f of n. So this is the set of all languages that are solved in order f of n time by a deterministic Turing machine. Deterministic. Okay? So what about regular languages? If I give you an input of length n, how long does it take order of for a DFA to check whether a given input of length n is accepted or not? Order n time, right? So in fact, all regular languages, because of this, are in time of n. Right? Because then I can just run for order n time and we're all set. Okay. And then we saw that 0 to the n, 1 to the n, 2 to the n, and at least 0 is in time of n squared. Right? Because there's a little technical issue here, but essentially, if we're given an input of length n here, then we can verify in n squared time whether or not it's of the form 0 n's, n zeros, n ones, n twos. The issue is that the n on the left side is not the same as the n on the right side, but it's okay because we have the order here. So we can strip out constants if we need to. So any questions on those two examples? What about this? So if I have constants C and D, how do time of n to the C and time, I should say, and C is strictly less than D. How do n to the C and n to the D relate to each other? Well, it's contained within, right? So every language that's decided in n to the C time is certainly decided in n to the D time because it's order of that amount of time. So in fact, this is a subset. We'll eventually show that, in fact, this is a strict subset with something called the time hierarchy theorem if we have enough time for the really cool stuff. But this is certainly a subset for sure because I'm giving you more time, therefore you can recognize potentially more languages. That's all I'm saying. Okay. And then now let's talk about one of the most misunderstood things in computer science ever. Let's define P to be the union over all k at least 0 of time of n to the k. So P here stands for polynomial time. So I'm just going to write that. So why do you think that we would want to look at this set of languages that are in P? So for a long time, what people were looking for are efficient algorithms to solve problems. And for a while, this was not really a well-defined thing until the 50s, 60s, and 70s, where people said, oh, we have these algorithms that run in polynomial time, and then we eventually implemented them on computers, and they ran pretty fast. So what people noted as efficient was equivalent to saying polynomial time. But is this still true? Not necessarily. Who remembers bubble sort? What time is that in? N squared time. Is this an efficient algorithm? No one in their right mind, there's actually a very technical reason why someone would want this, but the vast majority of people would not want to implement bubble sort because there are faster algorithms for the actual asymptotic time, like it runs in n log n time versus n squared, but also when it's actually implemented, it's a lot faster than bubble sort is anyway. So there seems to be a contradiction, a distinction between what is efficient on a normal computer versus, or a modern computer, versus what is efficient in this sense, right? So we are going to, for the moment, going to say that P represents efficient algorithms. But just take note that in the real world, this is not the case, okay? So there are actually some compilers that say you can never have a check-in where an algorithm has n squared time in it. It needs to be faster than n squared. But each of those is polynomial time. If I have an algorithm that runs in time of n to the Google, GOL, not the company, but is this a polynomial time? Yeah, because it's n to some number. So, but obviously no one would ever want to implement such an algorithm, right? Because it's incredibly slow. But so just, it's a red herring to say that P represents efficient. That's all I'm saying. Any questions on P? Okay. So one example of a relation between what CFLs recognize versus what decidable languages are is this. So I'm only going to outline this. I'm not going to give every detail. But every CFL is in P. So remember the A sub CFG algorithm. We converted the grammar into CNF. You can show that takes polynomial time. Then we looked at every single derivation of length 2n minus 1, right, on the input. And then we just checked if any of them work. Is that a polynomial time algorithm? No, because you can actually see the exponent in the runtime is not a fixed integer. It depends on the input size. And so therefore is not a polynomial time algorithm. And it's actually very slow. So what do we do instead? Well, if I have a context-free language, do I have a context-free grammar for it? Yeah, of course. Yeah. So this is just going to be a sketch of it. So if we have so let L be a CFL, then of course from that exists a CFG for L. But I'm going to insist that it be in CNF. So this is actually another useful application of CNF. Okay, so the grammar here is going to be fixed in size. So it doesn't matter really how much I use the grammar as long as I use only a polynomial, or I run in polynomial time in the size of the input. Okay, the input is what counts here. The size of the grammar does not count because I just keep feeding other strings, the grammar stays the same size. Well, how do I check whether a given string of length n, for example, actually is in the grammar? There's actually no reason to use a PDA in this case. But like if I have a grammar, yeah, the issue there is that if you convert it to a PDA, you guarantee, because it's in CNF, that the PDA will not run forever. But the issue is, can you bound the runtime of the PDA? And it's actually quite difficult because of the stack thing. So that's why grammars are easier in this case. But it is a good thought. Yeah.
Mark all variables in the CFG.
What's there?
Mark all variables in the CFG and see if the start variable is also marked.
That's essentially what we're going to do. But let's see. Let's step back for a second. If I want to look at a string W, for instance, let's say W1 through Wn, what could I show to you to certify that this grammar actually can make this string? I can make a derivation or a parse tree. So this is actually another use of parse trees. So let's look at a potential parse tree. It may not look exactly like this, but this is just another artist's conception. Okay. Well, let's see. Pick an arbitrary variable down here in the parse tree somewhere. can it make the empty string? No, it must make the entire string, right? Well, actually, we're not actually given this parse tree because I don't know on this input whether the grammar makes this string or not. So, but we got to figure out what could we do instead. Well, let's see. Well, we found out just from that analysis that this variable a must make something of the string, right? But the issue is, what part of the string does the variable a make? I don't know. Well, could we try all possibilities? Well, it makes something, let's say from wi to wj. I don't know where this is, but if a actually does make something of this string, well, could I just try all possibilities of I and j? Well, how many possibilities of I and j are there? Well, I have order n possibilities for the I. How many choices for the j? Order n also. So I have how many in total? Order n squared in general. So order n squared possibilities. Okay, so then from there, what we do is so now I actually forgot the algorithm. Let's see. Oh, okay. Yeah, here's what we do. So let's look at a rule like S goes to A and B. Well, this is a grammar in C and F, so a rule like this most likely exists. So then what we do, as I'm just sketching this, is we try all the possibilities of what A could make and what B could make. And then we just see, oh, does S actually make the string now? And the way we do that is the marking strategy that was given earlier. Well, if variable A, for example, it makes exactly one character, say wi, then we can say that A makes wi of the string. Well, then if we have A goes to BC, and then we know what parts of the string that B and C could make, such that, for example, if we know that B makes, I don't know, wi through wj, and we know that C makes from wj plus 1 through wk, for instance, then do I know anything about what A could make? wi through wk. So what we're going to do is, just as a sketch, is a dynamic programming approach, where we say, oh, this part of the string, this variable can make it. And then I just look at another rule and say, the two variables on the right-hand side, are they compatible with each other in the sense that do their indices differ, the end of the first and the start of the second only differ by 1? And then if so, I update the variable on the left side. I keep doing this over and over and until there are no more updates. And then I say, does S make W1 through Wn? Which is the string. And so therefore, I can check whether or not the grammar can actually make the string in polynomial time. And you can actually bound the runtime here, but the key is that the dynamic programming approach runs in a polynomial amount of time, because all you're doing is looking at a polynomial number of possibilities and then just updating a table based off of that. Other questions? Yeah.
So the wi through wn, I understand that's for n squared, but wouldn't looking at the variables add to that as well in like your parse tree?
A great question, but the grammar is fixed in size. So the input here is the string w of length n. So the grammar is fixed, so looking through the grammar takes constant time. You could parameterize the size of the grammar, but that's hardly ever done. We always look at the input size, the string itself. Yeah?
It's a time set that's describing how long the decider would take for one particular input. Right?
So this is not real. I didn't really define this formally, but O of f of n time is that all inputs of size n, I should say. Yeah, I actually should say that. So for all inputs of size n. Yeah, you're absolutely right about that. It's not just one input, it's every input.
But okay, so any input you put in there, it would decide it in
F of n time, yes.
But it's not going to be all inputs. I mean, you can use any input to get it, but not like all of them. You're not testing the entire language.
No, right, yeah.
Okay.
So it's like no matter what string of fn I give you, your algorithm runs in f of n time.
Okay.
Yeah, for all n, obviously. Yeah. Other questions? Yeah, because that's the big O thing. Yeah. So it could be that one string takes forever and all the others take a short amount of time. Other questions? And that's actually one of the big research questions is just a little insight. How do you actually measure the average case in terms of, so maybe some inputs take a really long time and most of the rest take only a very short amount of time. So how do you actually figure out when that's the case is a big open question. So I'm not going to solve it here, but it's just something to think about. And there are real algorithms that fall into this category. Other questions, though? Okay, so we talked about P, this class of languages solvable in polynomial time. What is the big famous question about P and something else? NP. So what does the NP stand for? It's not actually not polynomial. So we've talked about something TMs where the word starts with N, and those are called non-deterministic. So that's actually what the N stands for NP. So let's talk about that. So we're going to define a very similar class. Very similar class called N time. Same as time f of n, but this is non-deterministic Turing machines. So this is for non-deterministic Turing machines. And we insist that it could be for a non-deterministic machine that one computation path is really short and goes to accept, and some go really long, right? Because we saw this issue when we talked about recognizable versus decidable languages, when we tried to simulate non-deterministic versus deterministic. We tried to simulate the non-deterministic machine by looking at one transition, two transitions via the breadth first search strategy. So what we're going to insist here is that every computation path that you could ever take takes at most O of f of n transitions. So, and here we insist that every computation path that you could ever take takes order f of n transitions or steps. But the notion is exactly the same, but just for non-deterministic. Any questions on that? Yeah.
Just to refresh my mind, but a non-deterministic TM doesn't exist in reality.
Correct.
Okay.
But
so
we're
it
going.
has to be simulated by parallel.
But the thing is, the whole reason we've been talking about non-determinism is that there's an equivalent formulation for NP, which non-deterministic polynomial, which is very relatable, that we could actually implement. It's equivalent to the non-determinism. So we can do away with non-determinism and deal with this easier one that can show a lot of results that we're going to show in a bit. But any other questions? And as you might expect, NP is the union of k at least 0 of n time, n to the k. Right. So the famous conjecture is that P is different from NP which means that there are languages that take more than polynomial time that are in NP. But of course, that's literally the million-dollar question. So most people think that it is true that they are different. I'm one of them, but no one's proved that yet. And there's a substantial amount of evidence to support that hypothesis. So let's actually talk about that quickly. A very simple result that we can prove in like one line is P is a subset of NP. Well, why is that true? So it should be pretty straightforward. Yeah.
Well, NP is something's an NP of a certain time, and that means it could be solved in that much time.
You think of it the other way. If you can solve it in deterministic polynomial time, you can certainly solve it in non-deterministic polynomial time, right? You don't need non-determinism to necessarily to solve the deterministic problem. So any deterministic Turing machine in polynomial time, nomial time, is also a non-deterministic TM in polynomial time. So that should be really straightforward. But of course, I would love to prove to you that this is actually a strict containment, that there are some languages in NP that are not in P, but I don't know of one. And neither does anyone else in the rest of the world, despite what some people actually claim. So this is actually the territory where we start finding things that we don't know what the answer is. So here, I don't know the answer of whether they're different or not. We know all the answers about DFA's Turing machines, well, most of them that we encountered, context-free languages, but here, we don't know the answer, which is kind of sad, despite 30 years of research. What's there? Yeah, and there's actually a substantial amount of evidence to support that they're different that we'll get to pretty much the rest of the class, and along with other results too. Cool. Let's see. So as the suggestion was, we can't actually implement a non-deterministic algorithm, right? Because we don't have non-determinism guessing. So what we want here is that could we actually try to verify whether something could be done in non-deterministic polynomial time. So for example, so let's say that one of us is trying to solve the primes problem, right? Where you're given an integer and you want to check whether it's prime or not. And so what could be a convincing proof to you? Like, you give me an integer n, how could I prove to you that, for example, this number is not prime? Find two divisors, right? Because multiplication is super easy. But could I potentially be evil and give you like bad possible divisors? Like if you ask me if 10's a prime and I tell you 2 and 6, should you say that those two are divisors of 10?
No.
No, why not?
You can quickly check.
Because you can quickly check the multiplication and verify for yourself that what I gave to you was garbage. So that's actually an equivalent formulation of non-determinism here. So what is the formulation here? So you give me an input, and I'm going to magically, in some sense, give to you a certificate of whether or not that number is prime, or 0dn, 1dn, 2dn is a member of this language, right? So it's a certificate to you, a proof of some sort that you can quickly check in polynomial time, deterministically, okay? So I'm not going to prove it here because you can look in the Sipser book for a proof of this, but the proof doesn't actually get anything insightful out of it. It's just an application of the definition of non-determinism. But NP is equivalent to the following notion. Okay, so we're going to say a verifier is a deterministic Turing machine that on input, here I'm going to give you two strings, W and C. So going back to our example, here the W you gave to me, and I gave you back W and C. So I gave you the certificate C and the original input back. And then your task as the verifier is to verify whether or not W is in the language using this certifier, this certificate. So here is a Turing machine, let's call it V. Oh, actually, that's a bad name. Turing machine Z, that on input this, if Z accepts it, then W is in the language that we're concerned about. So like primes or something like that. So I'm giving to you back the original input you gave me and a certificate that you need to check in polynomial time efficiently whether or not W is actually in the language using that certificate. And we'll go over examples of like what a certificate actually looks like. But it's just a proof of some kind to verify whether a string is in a language or not. So like a proof for the primes problem would be or proof that it's not a prime would be the two strings. The two integers that correspond to multiplying them and getting the original integer out. Okay, and then of course so I'm not going to write polynomial because I hate writing the whole word. So I'm going to say polytime verifier is one that runs in polynomial time. So it's pretty straightforward. Okay, and NP here is the set of languages with polytime verifiers. Okay, so like the primes problem, that's actually not an NP. So what would be one that is an NP? How about this? So this problem called the Goldbach problem, which is the set of all integers such that it is the sum of two primes. Okay, so all the integers that are the sum of two primes. So you give me an integer n. What could be a certificate to convince you that this number really is the sum of two primes? I give you the two primes, and then you just check for yourself by adding them, and if it equals the number you gave me, great. So that would be a certificate that you can check efficiently. What's that? Yeah, composites, yeah. So primes is actually, there's a huge history on primes. If we ignore the fast algorithms that are known for primes, it's actually in something called co-NP, which is the complement. So the complement of primes is an NP. It's actually NP, but let's ignore that. But any questions on this different definition of NP? Yeah.
So what's generating the certificate again?
So it's a magical thing.
Okay.
So it's not actually generating this. It's just any possible certificate that you're given, you can check it yourself. So like you look, you should be able to handle any possible certificate, and then just say, oh, this certificate can verify whether or not this thing is in the language or not, and always run in polynomial time.
Okay, so you see some way to define it.
Yeah.
It could be created.
Right. Yeah, and we'll do an example right now. But unless there are other questions, yeah.
Could you define P as the same thing? So like polynomial time verifiers.
That's actually an alternate proof that P is a subset of NP, because the polynomial time verifier in this case is just run the polynomial time algorithm, right? And the execution of that algorithm is the certificate, because it's only polynomial in size.
So that definition of NP though, so that you could say that about P as well, because P can, you could just use that P's algorithm.
It's a polynomial time verifiers. And I did not necessarily say polynomial time algorithms. So there's a verifier to check whether a certificate guarantees this thing is in the language, but the algorithm only gives you the input. It doesn't give you the certificate. And of course, this is the famous open question, right? It could be that NP has polynomial time algorithms. We don't know. So your question could be yes or no. No one knows the answer for sure. But we're defining NP to be only the verifiers. It could have fast algorithms, but we don't know the answer.
And that's equivalent to the definition prior.
Yeah, so the way that you do this is you just, in one direction, you non-deterministically guess the certificate, and then you run the verifier. And then the other way is very, very similar to that. So it's just an application of the definition of non-determinism, but I won't ask anything on that. Other questions? Yeah.
Verify be also defined as like a list of choices that a query machine makes rather than the non-deterministic becomes a deterministic one, which helps to verify.
The issue is that the deterministic Turing machine might not run in polynomial time. You're absolutely correct, but it's just the issue now is the time issue, right? So for space, that answer is actually correct, and we'll get to that. But for time, because you use more time in actually converting it anyway, you might not run in polynomial time. But for space, it's correct. Other questions? Okay, so let's talk about one problem of graphs. And this is actually something that I've come across a lot of these problems I've come across in my own research, believe it or not. So this problem is called the, depending on how you say it, I say it clique. Some people may say click. I say clique. It's a big deal to some people. So what is this problem? So I'm going to give you a graph, and I'm going to give you an integer k. Okay? Okay. What is a clique in a graph? Does anyone know? Right. So it's a subset of the vertices such that every edge is present in that subset of vertices. This problem says that there's a subset of size k that is a clique. So G is a graph with, I can define this even more formally than this, but a k clique. So if you are not sure about this, it's a set of vertices of size k, and every single possible edge is defined between them. Every single one. And if we're just trying to solve this problem normally, the algorithm's going to be given this graph G and an integer k, and it's you just have to determine, is there a k-clique or not? So what would be an algorithm for this? Ignore the certificate for a second. What's just an algorithm for this? How about we just try every subset of size k? Right? Just try every subset. So idea, try every subset of size k, and then for each one, just check if all the edges are there. What's the runtime of that? Well, let's see. how many subsets of size k if there are n nodes? N choose k, and then we can just be lazy and upper bound that by n to the k, as an example. So n to the k, and each one, although this is not really important, each one takes k squared time because I got to check k choose 2 edges, but that's upper bounded again by k squared. So this runs in order of n to the k times k squared time. So it looks polynomial to me, right? Why is this not necessarily a polynomial algorithm? Yeah. Not necessarily. K squared is polynomial in k. K is not a fixed integer, right? It is part of the input. If k was a fixed integer, this is a polynomial time algorithm. Like if k is 100, for instance, this is a polynomial time algorithm. So because it's part of the input, this is not necessarily a polynomial time algorithm. So there's actually a lot of research of whether even if k was varied with the input, but only k is small, do we still get a fast algorithm out of that? And maybe we'll talk about that toward the end. But this is not a fast algorithm. So let's say that you give me the graph and the k integer. What could be a proof to you that I found a k-clique in the graph? Found a subset. So I tell you k vertices. And then could you check deterministically whether every single edge in that set of size k was there? Yeah, that's pretty simple. So the certificate here is the subset, or not the, a subset of size k. And then the verifier checks whether all k choose 2 edges in this subset are there. And that runs in polynomial time because in terms of k. And so because it's just upper bounded by k squared, for instance. And so therefore, the verifier here runs in polynomial time, deterministically. So what can I say about clique, the problem clique? It's in NP. Great. No one knows whether it's in P or not. And we'll hopefully show some evidence for that. But it's definitely an NP for sure. Any questions on that? What's the next one? How about this? And so this next one, maybe I won't get to all of it, but I really come across this literally every day in my own research. In fact, it's almost all my research devoted to a problem like this one. So therefore it must be important. So it's called subset sum. And here, what we're going to be given is not that problem. It's in my notes, but I'm thinking of a different one. It's called set cover. So here, I'm going to give you a universe, as it's called U, which is just a set of elements. It's just a giant set. And I'm going to be given a bunch of subsets of U. So it's just a bunch of subsets of size U. But I'm also going to be given something else, an integer S, for instance. Oh, I shouldn't call it S. Let's call it A. And what we want to know is there a subset of size A that intersects all of the subsets? Okay? So, and exists a subset of size A that intersects all of the SI, all of the subsets that I'm given. So for instance, to make this more concrete, so let's say I'm given the sets 1, 2, 4, and 2, 3, 5. And the integer, let's say, is 1. Could you find a single element that hits both of the subsets? 2, right? Because that intersects both of the subsets. So there is one here. What if I deleted the 2 from the other one? Is there a subset of size 1 that works here? No. So in fact, that would be a no instance here. Is set cover in NP? What would be the certificate? The subset of size A. Okay, so what is the certificate? The subset of size A. Well, how could you verify that this subset really intersects all the other ones, all the subsets that you're given? Just check intersection. Yeah, easy. So verifier checks if intersection non-empty with all the SI. And that easily runs in polynomial time because you just look at each of the sets in turn, just find the intersection, which is easy, and then you're all set. So therefore, we can say that set cover, by the way, I have no idea why all the names are capital, but that's just a convention. Set cover is an NP. Yeah.
Why, if you have a verifier that it's empty?
Because the certificate is being given to you. If you wanted to just solve the problem, the certificate's not being given to you. So it's like you're non-deterministically getting the proof of whether this thing is in there or not.
But like, why does that ensure that the algorithm is an NP?
That's how we defined NP. So you can think of it as all the problems which have polynomial size proofs. So like the proofs are really short to verify whether they actually are a proof or not. That's another way to think. Any other questions? Let's see what time. Okay, time to go.